Building an AI that's powerful on paper, that's actually kind of the easy part. But making it truly learn and not just cheat by memorizing the answers, well, that's a whole different ballgame. It takes a bunch of really clever tricks called regularization, and today we are diving deep into that secret sauce.
First things first, we have to meet the main villain of our story. It's this incredibly frustrating thing called overfitting. Honestly, this is probably the single biggest hurdle that stands between a cool AI prototype and one that's actually useful in the real world.
So what do we do about it? Well, think of it like this. An AI model that overfits is like a student who's cramming for a big exam. They don't learn the concepts, they just memorize the exact answers to the practice questions. So yeah, they'll get a perfect score on the practice test. But the second they see a slightly different question on the real exam, they're totally lost.
So, to put it a bit more formally, overfitting is what happens when a model gets so good at the data you trained it on that it starts memorizing all the little random quirks and noise instead of learning the actual general pattern you want it to. And this huge gap between how it performs in training and how it performs in the real world, that's the problem we have to solve.
All right, so how do we fight back against this memorizing student? Let's take a look at the first line of defense. Some of the first, most intuitive ideas that engineers came up with to get their models under control.
Okay, here are two of the absolute classics. On the left, you've got L2 regularization. It basically punishes the model for being too complex. It's like telling it, hey, keep all your internal knobs and dials, your weights, small and simple. Don't get overconfident and rely too much on any single piece of evidence. It forces the model to find broader patterns. And then on the right, we've got early stopping, which is even more common sense. Just watch the graph. The blue line, that's the model's error on its training data. It just keeps going down, which makes sense. But the green line, that's its error on new data it's never seen. And see that red arrow? Right there, the green line starts to go back up. That's the exact moment overfitting kicks in. So with early stopping, we stop early. We pull the plug right at that sweet spot.
Now those early techniques are great, they're like the basic guardrails. But the next real breakthrough came from a super powerful idea: teamwork.
And this leads us to what's called the ensemble method. The logic here is just beautifully simple. If you have a really tough question, you don't just ask one expert, you get a whole committee of them together. So here, we train a bunch of completely different models, and then we just average what they all say. As long as they're all making different kinds of mistakes, the wisdom of the crowd takes over, and the final answer is usually way more accurate. It's incredibly powerful. But, and this is a big but, it's also incredibly expensive. Training and running dozens of giant models is a huge computational headache. This is the exact question that led to one of the most brilliant ideas in modern AI. What if you could get all the power of that huge committee of experts, but without having to pay for it? What if you could get it all from just one model?
And the answer is a technique called dropout. The idea is so simple it almost sounds crazy. During training, at every single step, you just randomly turn off or drop about half the neurons in the network. They just go dark. It's like forcing your team to solve a problem, but every time they meet, different people are randomly told to stay silent.
Now this is what's so cool. Here's why that crazy idea works. By randomly shutting parts of the network down, you make it impossible for any single neuron to become this superstar that everyone else relies on. The network can't get lazy and just depend on one feature, like say, has pointy ears, to know it's looking at a dog. It's forced to learn a bunch of different, more robust features, the eyes, the tail, the paws, because it never knows which neurons are going to be available at any given moment. And this slide really nails the big picture. Every single time you drop out a different random set of neurons, you're essentially training a new, slightly different, slightly smaller neural network. So over the entire training process, you're secretly training thousands, maybe millions, of unique little networks that all happen to share the same underlying DNA. Dropout is this incredibly clever, super efficient hack to get the power of a giant ensemble inside just one model.
Okay, so we've talked about controlling what a model learns to stop it from memorizing. But now we need to pivot because there's another equally crucial problem: controlling how it learns. This is all about making sure the whole training process doesn't just fall apart.
For years and years, there was this massive roadblock that stopped us from building really, really deep neural networks. Here's the problem. As the data signal passed through layer after layer after layer, it would either shrink away into nothing or it would explode into ridiculously huge numbers. Look at that top row of graphs. The signal is basically flatlining to zero. That's called the vanishing gradient problem. And when that happens, learning just grinds to a complete halt.
The game-changing solution to this is a technique called batch normalization.
The best way to think about it is like a tiny signal regulator that you place between each layer of the network. So, after a layer does all its math, batch norm steps in and basically cleans up the signal. It recenters and rescales it, forcing it to have a nice, healthy, consistent distribution before it gets passed on to the next layer.
And the impact of this one idea was just staggering. I mean, look at this chart. The red dots, those are the major AI models from before 2015. You can see they're all hitting a wall. Their error rates are stuck. Then, batch normalization arrives on the scene, and boom, look at the blue dots. Suddenly, the error rates just plummeted. This one technique is what finally made it possible to train the kinds of ultra-deep networks that power the entire AI revolution that we're living through right now. It was a massive milestone.
But it's not quite a one-size-fits-all solution. Batch norm is really just one tool in a whole family of normalization methods. The key difference, like this table shows, is what data they're looking at to do the cleanup. Batch norm looks across an entire batch of different examples at once. But something like layer norm, which is absolutely essential for models like transformers, the things that power ChatGPT, it normalizes across all the features of just a single example. It's a subtle difference, but picking the right tool for the right kind of AI is absolutely critical.
So let's bring this all together. The most important takeaway is that these techniques aren't competitors. They're all part of one sophisticated toolkit. Engineers will use the simple guardrails like L2 and early stopping to prevent the basic memorization. Then they'll use clever tricks like dropout to force the model to build really robust features. And all of this is built on top of a stable foundation provided by things like batch normalization, which makes training these massive models possible in the first place.
So, we've explored the secret sauce, the bag of tricks that took AI from being a simple memorizer to a genuine learner. These are the techniques that let us build and control these unbelievably complex models. But it leaves us with one final and, I think, fascinating question. As these AI models continue to get exponentially more complex, what happens when they become too complex for even these tricks to tame?